Hey, welcome back, beautiful students. Welcome back to part 2 of simple regression and correlation. So, where we last left off, I had discussed the terms that you see in the model. So, this is an annotation of the model. And if you page down, I actually want to refer you a few slides down, you'll see that the same model can be written out in different ways. So these are the different notations of the same line model. I'll remind you what this represents, this equation that we see there. What that represents is the relationship between two variables. What we are doing is regression, and regression explains the relationship between two variables. One variable being the independent variable and the other variable being the dependent variable. And what we expect, the reason why we're doing this type of analysis, is we want to try and find out if we manipulate or if we make a change in the independent variable, what is going to happen to the dependent variable. And once we've gathered data and we've done this, some calculations on the data, we'll come up with a line model which we write down like this, and we use this model to communicate this information to others. So others understand what this model means because they understand the terms that we discuss and the terms that I'm referring to is that we dealt with in the last screencast, which is basically the y-intercept for the population. And the y-intercept is when the independent variable or x is 0, that is where y crosses the value that y is. Or if we look at it on the graph, where y crosses the line. And the slope, which is the for one change or movement in the independent variable x, what is the change that we expect to see in the dependent variable y? And so on the next slide, I have discussing the model and the three terms, which is what I just explained now. The slope being the I beg your pardon, is the expected increase or decrease in the dependent variable y as a function of the increase or decrease of the independent variable x, and the intercept is the expected value of the dependent variable y when the independent variable x is 0. And the error term known as the residual is not something that I'm going to deal with in Stats 3. So what we will basically do is we will focus on notations of the equation that looks like these three, where y is equal to a plus bx, this being the y-intercept, and that being the slope or the gradient. And it can also be denoted as alpha and beta, or B0 and B1. So take note that the A is the same as alpha, is the same as B0. And different people, in industry you'll find that different people write it out these three different ways, but it all means the same thing. Similarly, B is the same as beta, is the same as B1. And now I know you were thinking, now what on earth has this got to do with what we are going to do? Well, what we're going to do is, we work with samples, which represents population, etc., etc., etc. You know that spiel, that whole story, that sing-song that I always do. So to develop this model, to communicate to other people about this relationship, we're going to use a data set. So we are going to use a set of observations, which is part of a data set, otherwise known as a sample of data. And this data will have X values. This data will also have Y values. And then using this data, this could be historical data that you've taken from years ago, or months ago, weeks ago, even today. But if you have this set, then you can calculate this. Now to calculate this, I start with B1, which is my slope. And to calculate B1, I need to find something known as SSXY and SSX. And that I obtained from my data. Now, for exam purposes, I'm not going to expect you to do the calculation that I'm about to show you. exam purposes, I am not going to expect you to do the calculation that I'm about to show you, but I need to show you this so that you have an understanding of how it is obtained and that it's not just thumb sucked. SSXY, when we put the table in, or when we put our data in a table like this, and it's best to use Excel to do that. So I've got an Excel spreadsheet of an old example that I did a few years ago. I'm going to move my screen around a bit to try and show you what's happening here. Okay, let me make that a bit bigger because I'm sure, well, I can't even see what's going on there at that size. Okay, so this is an old example that I had. And the example that I did was a market day at a school. And I said the amount of profit, I said there were 20 students that took part in a market day. And each of these 20 students did a certain amount of planning for this market day. So each of them made a product and they needed to plan their product, and the amount of profit that they obtained as a result of the market day is my dependent variable. So my planning hours is my independent variable and the profit is the dependent variable. And so what I do is I put it in a table like this, a cumulative table like this, and I've got to calculate independent variable squared profits, which is y variable squared, the products of the independent, which is the independent variable, times the dependent variable. So I've got a column of all of that. Then I have each individual observation of my independent variable minus the x bar, which is the average of the independent variable, the square differences of that, and then the same for the y bar. So once I've done all of this calculations, then I'm ready to calculate my SSX and my SSXY. And I also, actually, funny enough, I do that on Excel, but let me explain to you how I do that. SSXY is actually the sum of the products of all the x's and all of the y's. So if I go back, let's cancel that, I'm so sorry. If I go back to that, you see here are the products, all of my x's and all of my y's, so x minus y for all of them, and the product is that jobby over there, and then I subtract that by the sum of the x's. So the sum of the x's is adding all of those x's up, timesing that by the sum of all the y's, and then dividing it by the number of observations, and that calculation will give me SSXY. SXX is the sum of all the squared x's times the sum of all the x's, which is squared. So all the squared x's, let's see, where are the squared x's? Profit squared? No. Is profit squared? No, that's y. Profits is y, so it's not profit squared, it's planning hours squared. So 20 squared is 400, 36 squared is 1296. And SSX is the sum of all of that squared x's. So the sum is this answer here. I've added all of that up to give me the sum. And then I subtract the sum of x's. This is the sum of the x's. And then I square that number. And I divide it by the number of observations. And that gives me SSX. But again, I'll reiterate that I'm not going to ask you to do that for an exam question, but I just merely needed to explain to you where this SSXY and where this SSX comes from. And once I have those two values, then I use that information to calculate my slope. So in an exam, I will give you SSXY and I will give you SSX, and you will use this formula to calculate the slope. Once you have the slope, you once again use your data to calculate the y. And to calculate the y, you use a variant of that line equation, which is basically B0, which is that the intercept or the term that I'm looking for, And remember I just said earlier, you're using your data, you're going to use all of the y bars. Y bars means the averages of all the y's, and you're going to use the information, all of the x bars, and you're going to use the slope that you've just calculated. And the answer of this will give you your intercept. So then for a particular set of data, you will have calculated the line formula, which represents the relationship between the two variables that is reporting, that the data set is reporting. And so that, my dear students, is how we calculate the line formula that represents the best fit to describe a relationship between a two variables in a data set which represents a population. And reading what's on our slide, understanding the least squared method to obtain the best fit, it is the most common approach to finding the unknowns, and those are the two terms, the slope and the intercept, in an equation. Is the method of least squares. This method minimizes the sum of the squared differences between the actual independent variable observations, which is y for each interval, and the predicted value of y for a particular observation, and it uses a simple linear regression equation. Of all the possible prediction lines, remember I drew that little picture for you of possible prediction lines, which could reflect the relationship between x's and y's. This method provides us a way to select the line where the error, the residual, is known as the error, where the error is kept to the minimum, or basically the deviation away from the line is kept to a minimum. And so once we have this line formula, then we are able to interpret, we're basically able to make predictions about the variables using the line, because we say that this is the relationship between these two, and so we can make predictions what's going to happen to the x if we know the y, or what's going to happen to the y if we know the x, and we can interpret things based on this line model. So here is an example, but I think I'm going to end this screencast now. And when I start the next screencast, then I'll explain with the help of this example. See you later, alligator.